All right, so we're here for the second part of chapter 3. We're going to get into energy in just a second, but I want to talk to you about the law of conservation of mass, or law of conservation of matter. It says that no new matter can be created and no existing matter can be destroyed. It just changes form. So this means that if I burn something, it doesn't go away. It just turns into other stuff. So if I burn some wood, it's got carbon in it, it turns into carbon dioxide because it's reacting with the oxygen in the air. Now you can have changes in mass and nuclear reactions, but we're not going to talk about nuclear reactions until chapter 5 for Chem 2A, and we're not going to talk about it all in Chem 19. But we can, they're very, very small changes, and so we can essentially ignore them. So what this means is that if you burn something like butane, the mass of the products and the mass of the reactions is going to be the same. So like if I measure the butane and oxygen I was using in that lighter, and I measured the carbon dioxide and water that I made when I burned it, they'd have the same mass. The same happens with energy. So we're going to talk about energy as we finish this chapter. Energy is the capacity to do work. Energy is the reason why anything does anything. So the law of conservation of energy says that energy is just transformed. It's neither created nor destroyed. And then here's some energy comparisons just for you to kind of get an idea of what we're talking about when we talk about energy. So some units of energy that you need to be familiar with. This is not a table in your textbook, but it is a good table and I wanted to use it. The SI unit for energy is the joule. But we use calories as well as kilocalories. And so take a look at this. There's a big C calorie, and that's 1,000 little c calories. So the reason why this is a thing is because in the US, we don't use the metric system. And if I tell you to eat 200,000 calories every day, that's too big of a number for you to keep track of. So I tell you 2,000 kilocalories. So when you're counting your calories and you're using food in the US that has calories on it, you're probably using kilocalories. 1 kilocalorie is equal to 1 big C calorie, which is equal to 1,000 little baby calories. Look on the back of your nutrition facts, it's a capital C for consuming kilocalories. But it is a unit of energy. Calories are calories are calories. The calorie is not different if it comes from fat or if it comes from carbs or if it comes from protein. It's all the same. It's just that fat puts more calories per gram of food. So if you are trying to consume a lot of calories, reach for something high in fat. If you're not trying to consume a lot of calories, then don't reach for something that has a lot of fat. Now, your body chemistry is much more complicated than that. So there are lots of other diets and things that you need to be aware of, and you have to make sure you get all your right nutrients. But essentially, a calorie is a calorie is a calorie. If you're just looking to count calories, it doesn't actually matter what you eat. Now, of course, that's just body chemistries are different, right? So like, if I eat too many carbs, my body is like, what are you doing? But like I can have as much fat as I want and it's fine, right? But like, there are other reactions besides just like calories that happen in our body. So, but as far as like, just counting calories, it doesn't actually matter where we get them from. If you're getting all the nutrients that you need. So different types of energy, y'all are probably familiar with some of this. We're gonna look at potential energy. And chemical energy is a type of potential energy, but calorimeters, how do we get those calorie values in the back of your nutritional facts? What we do is we burn the food in presence of oxygen to do a combustion reaction. And then the energy from the food being burned is transferred to the water. The water starts increasing in temperature and we measure it with the thermometer. So this is just kind of how we measure these calories. Here's my little kilocalorie and here's the little nutrition facts. So you can see that capital C here, tricking us into those kilocalories there. And oh, look at that. What is that? Ooh, it's a conversion. Can you put that in a conversion? Can you tell me how many kilocalories per gram for carbohydrates. Oh yeah. Carbs are going to have 4 kilocalories equals 1 gram. That's a beautiful conversion right there. Or you can say 4 big C calories is equal to a gram. Or you could say 4,000 little calories is equal to a gram. Either way. And these are kilojoules, so we also use joules. So here are just some composition for different foods. Let's see where their calories kind of come from. But our main focus is going to be potential energy. So I want you to think about potential energy as like, if I keep a 10 kilo weight at the top of a building, it has high potential energy. And in chemistry, high potential energy means it's unstable. And then low potential energy means it's stable. So if I have some reactants that have a lot of potential energy, they have a lot of stored energy. Okay, so potential energy is stored energy. If you have a lot of stored energy, you're going to want to spend it. You're going to want to fall until you're stable. It's like if I just hand you a bunch of cash, probably going to want to use it, right? So the chemicals are kind of like that. They have the stored energy, they want to use it. So they're going to go towards a more stable, low energy state. So if you start with your reactants high energy, they're going to release energy to get to products. But if you want to make something higher energy, like if I want this weight to go down, all I have to do is drop it, right? It's just going to happen. This reactants are just going to make products because the energy is released. Now this is very oversimplification of what actually happens, but energetically, the idea. But what if I wanted to get the weight back up to the roof? I have to put energy in to do that, to carry that thing up the stairs or lift it up or something, right? So it takes energy to move things up to higher energy, and it releases energy to move things to lower energy. So we call these endothermic and exothermic. And I want you to think about exothermic. What this means is exiting, and thermic means energy or heat energy. Really means thermal energy. We think about it as heat energy though. Heat energy is exiting, so it's released. Exothermic. An endothermic reaction is the opposite. I want you to think about entering. And then thermic is heat energy or thermal energy. So the energy is entering the reaction. It's being absorbed by the reaction. Let me ask you this question. Going back to where you can kind of see both endothermic and exothermic. If inside my can of bubbly here was a exothermic reaction, the reaction inside the can is releasing energy, what would I feel when I touched it? I would feel hot. Yes. So if you are doing an exothermic reaction, okay, exothermic reaction, energy is released. If you are touching that where the energy is released, the energy is released into your hand. So if you have a reaction in a test tube and you want to touch it, wow, I have way too many fingers, looks like. The energy is going into the hand. It's going to feel hot because the reaction, RxN, is releasing energy into my hand. On the opposite side, if I have an endothermic reaction, the reaction is taking in energy. And where does it get that energy from? My hand. So it's going to feel cold to me. So if you use a hot hand pack or a cold pack, that kind of where you press a button or something or shake it and it gets hot or it gets cold, these are either endothermic or exothermic reactions happening inside of that hand packet. So thinking about endothermic and exothermic as we change phase, anytime you add, you need to add space. So going from solid to liquid, liquid to gas, you would need to put energy in. So adding space between particles, energy in endothermic. If you are removing space, you need to slow the particles down, go back together. That's going to be exothermic. So when I freeze something, it's exothermic. That's what my fridge is doing. It's pulling all that excess energy out and pushing it out to the bottom of the fridge. So it's pulling the energy out of the water to freeze it. I'll let you look through this if you want to look at the slides, but it just kind of shows you how in hot water things move faster. So this idea of hot water, things are moving faster, gives us a definition of temperature. So temperature is a measure of this thermal energy. Thermal energy is the kinetic energy of molecules. What is kinetic energy? It's the energy of movement. So if my particles are moving faster, they have a higher thermal energy. If they have a higher thermal energy, they have a higher temperature. Literally what your thermometer is measuring is how quickly particles are touching it. If the particles are touching the thermometer a lot, transferring energy into the thermometer will rise because it's expanding because particles inside the thermometer are taking on that extra kinetic energy. So heat is a transfer of thermal energy. Heat and temperature are different. They're not the same thing. And temperature doesn't even measure heat. Heat only occurs if you have a change in temperature or a transfer of energy. So two ways in which you can have heat. There's a temperature change or there's a transfer of energy. So if I put energy in to separate particles, I have heat, using the energy to pull these particles apart. Or if I put energy in to speed up particles, that's also heat. So speaking of temperature, you have three different ways to think about temperature: Fahrenheit, Celsius, and Kelvin. Here are your three different scales here. I'm going to give you some equations. You have some equations in the back of your periodic table. Be familiar with those and be able to algebraically rearrange these equations. So want to give it a try and see if you can answer this question. So how would I solve this? If I have a Fahrenheit of -15 degrees, what is the Celsius? So I can use this equation here, and then I can say, well, Celsius is equal to Fahrenheit minus 32 over 1.8. So the first thing I'm going to do algebraically is multiply both sides by 1.8. So I get degrees C times 1.8 is equal to Fahrenheit minus 32, and then I can add 32 to both sides. And I just realized that I just rearranged that the wrong way, but it's okay. So now you have the rearrangement. It is Celsius times 1.8. I can write, I promise. Celsius times 1.8 plus 32. So being able to rearrange it is important, but we actually have it the way we want. So Celsius is equal, and I can put my -15 in, minus 32 over 1.8. So the rest of my work is here, 2 sig figs, because when I do the subtraction, I get to the ones place for my Fahrenheit, so that's where this is going to come in. When you're doing a quick note about sig figs here, this 1.8 is infinite sig figs, and the 32 is infinite sig figs, and the 273.15 is infinite sig figs. So the only thing that matters for sig figs is the temperature degree that you're using. So make sure that you're looking at that. So I'm looking at ones place here, so ones place here, and then this is 2, so this is also 2 because I'm doing a division. If you need some help breaking those steps down, let me know. So try this one. What's the body temperature in Kelvin if it's 37 degrees C? Okay, so working this one out, I know that Kelvin is equal to degrees C plus 273.15. Use that extra 0.15 if you can remember it. If not, 273 is okay. So I have 37 plus 273.15. So I'm going to write this out like this because it's going to help me with my sig figs. So I do my math. I get 310.15, but I have to cut it off. Remember, this is infinite. I'm going to cut it off here. So it's going to be 310, but I want to include this. So how can I do that? If I stick a decimal on the end, now I'm going to be counting from the Pacific side, so it makes all three of these significant. If I don't put a decimal on the end, I count from the Atlantic side and it's only 2 sig figs. I want the 0 to count, so I can either put a decimal or I can say 3.10 times 10 to the 2. So that's my answer here. That's why there's a decimal there. The last little bit we're going to talk about is heat capacity and using a heat equation with heat capacity. So heat capacity is something that sometimes students have a hard time with, but it's a very simple concept that if you have a high heat capacity, it means that you can take on a lot of energy before you start changing your temperature. It's essentially how resistant to change in temperature a substance is. So a high heat capacity means it doesn't really change its temperature very well. You put a lot of energy in, it doesn't change its temperature. Water has a super high heat capacity. Check this out. Water liquid, look at all these other things. 0.2, 0.051, 0.824. Water has a super high heat capacity, which is why it takes forever for water to get hot or to boil. Your pot, your aluminum pot, your iron pan is going to get way hotter, way faster. The water is going to take a lot longer to heat up. So that's what heat capacity is. Check out these units. Okay, you can rewrite this unit like this: joules over gram times degrees C. That's really what it means, or calories over gram times degrees C. It's a triple unit. Don't do any unit conversions with it. Don't do unit dimensional analysis with it. We're going to use algebra with it, okay, because it's a little too complicated for simple dimensional analysis. So the high heat capacity of water is the reason why you can put ice in a cooler and it keeps stuff cold, because it absorbs the energy from your food and doesn't melt. Also a reason why if you live on the coast, your temperatures are much more mild because there's a lot of water in the air, so it absorbs the energy from the sun instead of making the air hot. So here's the math. Heat is equal to mass times your temperature change times your specific heat. So I'm going to rewrite this a little bit the way that I'll show you, which is Q equals MC delta T, where your specific heat is also known as C. Temperature change is final minus initial. Any change in science is always final minus initial. So think about like, how do I know I've made a big change in my life? Or I get through the change and I look back and I go, wow, I changed a lot. Right? So you start from the end and you kind of look back to see what you have there. So specific heat is also known as C. So you'll see me just kind of refer to as Q equals MCAT. That's how it's written on your periodic table as well. So I get familiar with this version of this equation here. And these are all multiplied together. So let's try it. So how much heat, heat is Q. It's kind of important for me. Heat can't be H because there's something called enthalpy that's H, and that's thermal energy. So heat has to be something different. So they picked Q. I don't know. So try this question and see if you can figure out how much heat with these numbers. All right, let's work it out. So how much heat must 2.5 grams of gallium absorb from your hand to raise its temperature from 25 to 29? So let's identify some things here. Let me give myself a little page to work. So how much heat? So they're asking me for Q. So I'm gonna write Q equals question mark. And they don't tell me a unit for Q, so I guess whatever unit I get is fine. But if it's a multiple choice question, you wanna look for a unit, make sure it's not kilo or anything like that. You would have to do a conversion. They give me this 2.5 grams. What is that? That's the mass, right? So my mass is 2.5 grams. Then they tell me they're going to raise the temperature from 25 to 29.9. So what is my final temperature? That's going to be your 29.9 because it's where you end. And my initial temperature is going to be 25.0. That's where I started. So my change in temperature is going to be equal to 29.9 minus 25. Careful of my sig figs here. because I'm looking at decimal places when I do this math, right? And then I have a C. Look at how many C's are in this word. Capacity and specific heat capacity is a lot of C's. So that's how I can remember that that's C. They tell me it's 0.372 joules per gram degree C. And so this is important, a unit, because if I give you mass in kilograms, you have to change it to grams because you have to make sure you're using all the units of this number here. So let's do a little bit of math here. So I'm going to line this up 29.9 minus 25 because I want to make sure I get my right sig figs. So I get 4.9. It gets cut off here, so I'm going to use both of these numbers, but it looks like 3 sig figs maybe, but it's really 4. Or sorry, 2, not 4. And then I'm going to set this up. Q equals MC delta T, or Q equals MCAT. Let's plug in. This is my delta T. So my Q is equal to 2.5 grams. And my C, I'm going to put this in. Do not plug numbers in for this unit. Just use these numbers or these units after this number because that's where it goes. And I'll show you how these units cancel out algebraically. And then I have my 4.9 degree C. So look at how this cancels. I have degree C on the top and degree C on the bottom. And I have grams on top and grams on the bottom. And what am I left with? Joules. Isn't that a unit for energy? Sure is. So my Q is 4.557 and my unit is joules. Now what if I ask you for kilojoules? You can do a conversion after that. Let's look at my sig figs. So I have 2 sig figs here, 3 here, and 2 here. So I need my answer to be 2 sig figs. So I will say Q is equal to 4.6 joules for this question. Yeah. Plug in the algebra, chug out an answer. So you may be exposed to a heating curve or a cooling curve. We're going to focus on the heating curve, and then the cooling curve is just opposite. And this is like what happens if I take ice and I put it in a pan and I boil it, okay? So what we see here is kind of interesting, and I want to talk about a few points on this graph. So as I'm absorbing energy, what is happening to my temperature? So as I put energy in, let's start at solid ice on here. What do we see happening to the temperature? Right, it's going up, which means that what is happening to the kinetic energy of the particles? Their movement, also going up. So temperature, remember, is a measure of kinetic energy or movement. So if we're increasing our temperature, the particles are moving faster. Okay, and that's kind of important because we're going to compare it to something different. So I start moving my particles faster. I get to 0 degrees Celsius, which is the melting point for water. And then I keep adding energy, but what happens to my temperature? It stops changing. So I'm adding energy, but my particles aren't moving faster. Weird. Okay, but then I start adding energy again and my particles start moving faster. But then they stop moving faster. What is happening on these straight lines here, these flat lines? I'm putting energy in, but my particles are no longer moving faster. So putting in energy but particles are not moving faster. So what is the energy doing, do you think? The answer is the energy is separating the particles. Y'all, my particles like each other. They're attracted to each other. And so in order to separate my water particles, I have to put energy in to pull them apart. because they have these little magnetic attractions to each other. And so I got to put energy in to do that. That's what happens when you're at that boiling temperature. You're changing that, doing a phase change. So anytime you have a phase change, you're not increasing the temperature. If you don't believe me, get a thermometer and boil some water. It doesn't matter how fast you're boiling, how slow you're boiling, you're at 100 degrees probably if your water is pure. And you'll stay at 100 degrees until it all turns to gas. It'll stay constantly at 100. Pretty cool. Cooling curve is exactly the opposite, which is cooling it down. And then I don't like to focus too much on this, but you may see it in some of your homework, so I'll just kind of give it to you here. How much energy do we need to get through these phase changes? Well, when the temperature is changing, okay, so when I have a temperature change, I can use Q equals MCAT, right? Because I have a temperature change, but I can't use Q equals MCAT on these flat lines because there's no temperature change, but clearly there's still some energy being put in. So I have to use these heat of fusion and heat of vaporization. So fusion is a fancy word for melting. So how much energy does it take to melt ice? Well, it takes 80 calories per gram, or 334 joules per gram. Look at that beautiful conversion. Just use it as a conversion. If you're adding the energy, you're melting. If you're releasing the energy, you're freezing. You could actually calculate, if you put in this much ice in your ice tray, how much energy the fridge or the freezer has to pull out of your ice by using these numbers, if you're interested in doing that. Heat of vaporization, this is boiling or evaporating. So if I need to know exactly how much energy to boil some water, let's say I'm limited on the amount of energy I have. I only have X, amount of propane in my propane tank. Can I boil this water? I could calculate it. I can actually calculate that out. So it's going to be 540 calories per gram, or 2260 joules per gram, and just use it as a conversion. Don't try to get fancy with it. So we're going to do 2 little practice problems and you're done with this chapter. So why don't you pause and do this one? So how many kilojoules are released when 50 grams of steam from a volcano condenses? Now, at 100 degrees C, they're just telling me we're at 100 degrees C here because that means that I know I'm at that boiling point for water. It is not a temperature change though. So we're not using Q equals MCAT. So if I'm asking you for kilojoules, that means I'm asking you for heat. So I want to know what this is, but I'm not using Q equals MCAT. Why not? Because no temperature change. There's no change in temperature here. They give me a temperature, but if you read it carefully, it wouldn't change the temperature, just at 100. So what is it asking me about? It's saying, hey, you're here at 100. How much energy do you need to put in for this amount of water? So if I have 50 grams of steam and it's condensing, am I going to be using vaporization or fusion? So condensing is going from gas to liquid. And that is going to be heat of vaporization, but it's the opposite direction. We can't have negative energy though, so let's just use this heat of vaporization. So they asked me for kilojoules, so let's use this one. So let's use 2260 joules equals 1 gram of water. So I got 50 grams of water. I could set this up, right? But I need kilojoules, so let's write a conversion for that. So 1 kilojoule is equal to 10 to the 3 joules. So we can use our wonderful dimensional analysis. 1 gram of water is 2260 joules, and 10 to the 3 joules is 1 kilojoule, and that'll give us our kilojoules. And you should get 113, which is perfect sig figs, kilojoules of energy needed here for this process. Not a chemical reaction, but a physical change. Let me know if you have any questions about this. Like, text me right now if you have questions about it. Okay, so let's look at this. How many joules are needed to melt 32 grams of ice at 0 degrees C? So I want joules, so I want Q. So maybe I think I need Q equals MCAT. So let's see. Do I have a change in temperature? Nope. No change in temperature. just one temperature. So not that. If you're not using Q equals MCAT, you must be using heat of fusion or heat of vaporization. So melting, is that fusion or vaporization? That's fusion, because it's going from solid to liquid. So let's go grab that heat of fusion. You don't have to memorize these. I'll always give them to you. Now, do I want joules or calories? Ooh, I'm joules again. So I'm gonna use this one. 334 joules equals 1 gram of water. And I don't even have to do another conversion because I'm just asking for joules. So let's go ahead and set it up. Ice is water. So if that wasn't getting, sometimes that'll get people a little stuck. 334. I get 10,688 joules. Sig figs, I need 3. So if you wrote 107, you were wrong. I'm telling you I need 10,000. You can't tell me 107. If you want to use scientific notation, you can, but you gotta make it still 10,000. So here's your joules. If you want to put it in scientific notation, we can say 1, 2, 3, 4, right? But you can't tell me 107 because that's not 10,000. So make sure that you do not change your value when you do sig figs. All right.